All right, here we are again, except now we're in line. And so we're going to go back and actually revisit some of our discussion from Tuesday about the normal distribution. And so we'll be using just the calculators today, just like we did on Tuesday. I think we should probably save the Excel for the next time we're all together in the classroom, which is, of course, is a week from Tuesday. So in the meantime, we'll just keep working with our calculators. And if there's time, we may take a look at the exponential distribution, but we're going to focus our attention on really understanding the normal distribution because it is, after all, the one you'll see most often throughout the rest of your statistical career, I guess we could call it. So that's where we're going to start. Now, let me just get this open. Here's chapter 6. I'm also working on this document that I've been working on all morning that hopefully will help us understand more of the principles of the normal distribution. When we're done, I'll be posting this on Blackboard so you have a copy of it. And of course, the video will also be made available to you on both Blackboard and on my YouTube account. So that way you can pick it, go get it from either one. And that way, if you miss something or if anyone can't be here today, they can still watch and see what we did. Well, all right then. Now, if you remember last time, we were still in chapter 6. Now, 6 is our introduction to continuous distributions. And as we saw in the very beginning of the chapter, there's 3 that we need to consider: this uniform or continuous uniform distribution, which we've already covered, the normal, which we're part of the way through, but there's more details that I'd like to go over, and then the exponential, which is a little bit different. And that one, we may not have time to do more than just look at it this afternoon. In the other 2 classes, I just introduced it, but I didn't really get a chance to do any examples. So that's probably what's going to happen here. One of the unfortunate things about the exponential distribution is that you don't see it in the calculator, okay? It's not there. So for that one, we'll have to do all the work ourselves. But on the other hand, on the good side, the exponential and the normal are actually both in Excel. Okay, so that's very helpful. All right, so the normal distribution, if you recall, is characterized by this formula. And so that formula, when we graph it, ends up looking like a bell-shaped curve, as you can see here. And the normal distribution is characterized by 2 values. It has a mean and it has a standard deviation, which uniquely characterize its location and its spread about the center. Now, just to review a few of the key properties here. For one thing, the area under the curve adds up to 1. Okay, that's true for all probability distributions. And also, I want to add this to my graph. In spite of its appearance, the curve actually goes all the way out to positive and negative infinity. In other words, it doesn't ever actually stop, okay, which was not true, obviously, for the uniform distribution, which you recall was a rectangle. It was bounded within 2 intervals, or 1 interval with the lower upper endpoint A and B. But this one goes out and covers actually the entire real number line. So, and you can see also from the graph that it has a very important property. It is symmetrical about the mean. That's going to be very helpful in calculating probabilities as we go along. This idea of symmetry will be a huge help. And so we will take advantage of it whenever possible. Now, we also mentioned here that it is uniquely characterized by the mean and the standard deviation, so that in principle, there could be an infinite number of normal distributions, each with a unique value of the mean and the standard deviation. So as we saw when I was drawing them on the board, the mean is what tells us where it's located on the real number line. The standard deviation tells me how spread out it is. Okay, now we also introduced this very special case, the so-called standard normal, where we have a mean of 0 and a standard deviation of 1. Now, on your calculator, it's set up to assume that that's the one that you're interested in, unless you tell it differently. So as we go along, you'll see that often those are already in the calculator because they figure most of the time that's the one you'll want to use. All right, so with all that being said, we're going to review how to calculate probabilities under the normal curve. So, oh, you know what else I forgot to mention up here? With the standard normal, the letter Z is used to represent the standard normal distribution. And then for the others, we just use X like we usually do, right? In other words, it's most of the time, a random variable is represented as an X. This is the special exception because Z, you may remember we had this notion of the Z score on the first midterm. And that's because it's based on the standard normal distribution. So Z, when you see a Z, that means you're dealing with the standard normal distribution. For all the rest, we'll use an X. And you'll see as we go along. Okay, great. So for example, look at this one. Now, you can see it doesn't explicitly say so here, but we're looking at the standard normal distribution. Although I'm going to write it in here now. And you can see that it has a mean of 0 and a standard deviation of 1. And we'd like to know the probability that that Z falls between 1 and 2. Okay, now, as it turns out, that actually means the 1 can be interpreted as the mean plus 1 standard deviation. The 2 can be used to represent mean plus 2 standard deviations. So with the standard normal distribution, the numbers you see can be interpreted as how many standard deviations are we away from the mean. In case when they're positive, that means we're above the mean. When they're negative, that means we're below the mean. So what's the probability of being in that interval there? Great. So we did this several times on Tuesday. You go to your TI 84 and type in second vars, which is where you'll find all the probability distributions. Yeah, there it is. And then make sure you choose number 2, normal CDF. Okay. Now, do not confuse this with the first one, normal PDF. Do not use that one ever for any reason for this in this class and in the fall in stats 2. You will not use normal PDF. It's always normal CDF. Now, by the way, if you do accidentally choose the normal PDF, you'll know it right away because it's not asking you the right questions or the ones you would expect. So that would be a hint that you should move on to 2. And when you get there, you'll see that it's going to ask you, as you remember, for your lower limit, your upper limit, your mean, and your standard deviation. Okay, so we'll do that right now. And so these numbers result from the fact that this is the standard normal distribution. And like I said, they may already be in there, unless you've used this calculator for a different purpose recently. Now, once you have the lower limit of 1, upper limit of 2, the mean of 0, and standard deviation of 1, you go ahead and calculate it, and you should see 0.1359, which means 13.59% of the total area under the curve. Okay, so this is a perfect example of how to calculate a probability for the standard normal distribution. Now, I would like to point out to you, though, that because of the symmetry of the distribution, if you look in the upper right-hand corner, suppose I asked you now to calculate the probability that Z is between -2 and -1. Well, you can go through the normal procedure to calculate that, but if you recognize that these two shaded regions must be the same, you don't need to bother because you'll see that you'll end up with 0.1359. And that's again to this enormously important property of symmetry with the standard normal and all the other normal distributions. Okay. Now, of course, the chances of having this happen all the time are pretty low. Most of the time, the different problems will have completely different numbers, but once in a while, we can take advantage of this and speed up our calculations. Okay. Now, as far as the mind tap goes, I'm not sure what they're going to do. They'll probably ask you all of these concepts in one form or another. So we should be ready for anything that comes our way. It's going to be a while before you have to do this in MindTap, but you want to be ready for it. Yeah, in fact, I think I may try to make sure that nothing is due at the end of spring break. So yeah, it'll be a while before chapter 6 is going to be due. But anyway, let's come down here and look at this case. We've got the probability that z is greater than or equal to 1.50. So this time we're not looking at the area between two constants. We're looking at the area between a constant and positive infinity. And again, the fact that there's a z here indicates that this is the standard normal distribution. All right, so the question here is what to do about the infinity. Okay, the calculator doesn't have an infinity button. It's not possible to put infinity into your calculator. So we have to work around that by instead entering the largest number it's capable of expressing, which happens to be 1.0 times 10 to the 99th power. So how do you get that number in there? Well, the easiest way is to simply type second comma 99. So in other words, in this case, the lower limit is 1.5, the upper limit is infinity, which we will implement as second comma 99. And when you do this correctly, you should see in the window, it actually is replacing that with E99. This is how the calculator expresses scientific notation. So you see that we'll continue to use the mean of 0 and the standard deviation of 1. And if you do this correctly, you'll see that that shaded region is 0.0668 when rounding to 4 places, right? Good. So now, if not, that means there's a typo in there somewhere. By the way, here's a fun side note. If you reverse the lower and the upper limits, it'll give you the right number, but it'll make it negative. So if you see a negative probability, you should check right away to see if you haven't gotten your lower and upper limits backwards. Okay, it does happen. All right, so let's try this now. Let's look at the other side of this curve. Let's try the probability that z is now less than or equal to negative 1.50. So you'll type in the numbers. Now, of course, in this case, the lower limit is negative infinity. And the way to enter that into your calculator is to type negative second comma 99. And that will be replaced in this window there with negative E99. The upper limit is negative 1.50. And again, the mean is 0 and the standard deviation is 1. So you plug in all those numbers and you should see that within 4 digits of accuracy, you should get, again, 0.0668. Now, you already know why. I'm sure you know why this happened, because of our old friend symmetry. Okay, so anything above 1.5 will equal anything below negative 1.5. Also, a quick reminder, this 0 could be interpreted as the mean, and this is the mean plus 1.5 standard deviations. Whereas down here, this could be interpreted as the mean minus 1.5 standard deviations. All right. So, 1 second. Now, there's another probability that we can derive from this setup. If you look at it carefully, and again, I brought these together on this curve, you can see that the shaded region above 1.5 and below negative 1.5 will equal each other at 0.0668. Now, here's an interesting question. What if I need to know the probability that z is in between those two, between negative 1.5 and positive 1.5? Well, of course, I can go to my calculator and do it directly. And if you put in all those numbers, you'll see that you'll end up with 0.8664. But it turns out that wasn't absolutely necessary because the entire area under the curve is 1. Each shaded region is equal to 0.0668. So therefore, the area in the center could be thought of as 1 minus the probability that z is greater than or equal to 1.5 up here, on the right, and we also subtract the probability that z is less than or equal to negative 1.5 on the left. And by doing that, we end up with the exact same number, 0.8664. So you end up with this. And you can see that they do actually add up to 1. All right. So again, you've got two options for calculating this probability. Now, here's another one that we briefly mentioned the other day. What about the mean itself? What if I want to know the probability that z is greater than or equal to 0, which means the entire area to the right of the mean? Well, by definition, that has to equal a half, as is the area below the mean. Z is less than or equal to 0 also has a probability of 1/2. And again, that's because of the properties of this normal distribution. The two of them have to add up to 1. And because of the symmetry of the distribution, they have to equal each other. So the only way that can happen is if they're both equal to a half. Okay, so yes, you can type this into your calculator, although in this case, if you notice, you'll get a number that's ever so slightly different, which you can then round to 0.5. But just remember, the whole curve has an area of a half, of 1 rather. Each side has an area of 1/2. Okay, nice. So now, if you notice, the one thing all these examples have had in common so far is that they're all based on the standard normal distribution. Fine, but what about other cases that we may run into? In fact, most of the time, you'll actually be using other normal distributions. So now we started to do this example the other day. We have scores on an exam are normal, and we're assuming the mean is 80 and the standard deviation is 5. So I'd like to start out by asking, what is the probability that our score in the exam is 70 or less? Oh, actually, I just realized I wrote this incorrectly over here. Hold on. Yeah, this is backwards. Yeah, that's a lot more like it. All right, good. So now here, if you notice, this is the normal distribution, but it's not standard normal. Instead, we'll let X, and also you can notice we're not using Z anymore. X is the normal distribution. And in this particular case, it has a mean of 80 and a standard deviation of 5. That means we have to label our graph differently. And when we get to the calculator, we'll have to make sure that we change the mean and the standard deviation from 0 and 1. So in this case, I'm looking for the probability that my score is 70 or less. And if you want, you can think of that as the mean minus 2 standard deviations. Okay, because the mean is 80, each standard deviation is 5, so 70 represents 2 standard deviations below the mean. So let's come down here, plug in our numbers. We're going from negative infinity up to 70 with a mean of 80 and a standard deviation of 5. So I put a little arrow here to make sure you don't forget to change those. I think I mentioned this once before. If you do forget that part of it, the numbers you end up with will typically either be incredibly small or incredibly large. So you'll know right away something's not right. So the first thing you should do is double check and make sure you have the right mean and standard deviation. All right, so if you type in all those numbers, you should get, when rounding to 4 places, 0.0227. Okay, good. All right, so we're getting pretty good at this stuff, aren't we? Yes, we are. So now you can see where this is going. Let's try. Yeah, so here I've illustrated once again. This is the area that's more than 2 standard deviations below the mean. All right. And if you notice too, that's a very small number. The thing about the normal distribution is that even though it covers the entire real number line, the overwhelming majority of its area is within 3 standard deviations of the mean. The rest of it is so small, not that you should ignore it, but it has no real practical effect on our results. So the overwhelming majority of the area is within those 3 standard deviations, but it still does technically go all the way out to infinity on either side. Now, let's try this one. Let's go to greater than or equal to 90. And this now represents being 2 standard deviations above the mean. So when we type in the numbers, 90 up to infinity, which again, we represent as second comma 99. Well, what do you know? It's 0.0227 again. And that's not an accident because here with 90, we are 2 standard deviations above the mean. With 70, we're 2 standard deviations below the mean. So therefore, those shaded regions must be equal to each other. And that's due to symmetry. Our favorite property. Now, by the way, look what we could also do here. Although I didn't do it at the time, I'm going to try to sneak it in here somewhere. If I wanted to know the probability of being at 70 or above, it must be 9773 because that is 1 minus 0.0227. I thought I'd just throw that in there just as a quick reminder. Okay, so in other words, those two have to add up to 1. So we're not really using the property of symmetry. We're using the fact that the curve has an entire area of 1. Okay, now here is an interesting formula. This we definitely did not get to last time. Keep in mind that these wonderful little calculators we have not been around forever. The normal distribution was invented in the 18th century. So throughout most of the history of the normal distribution, nobody had calculators to help them calculate those probabilities. And there certainly weren't any laptops, that's for sure. So what did people throughout history do to calculate normal probabilities? Well, there are tables that you can find at the end of any statistics book. And those tables represent probabilities for the standard normal distribution. In fact, if you were introduced to statistics in high school, there's a pretty good chance that you were asked to use those tables. Now, there's just one problem with tables. I mentioned earlier that there's, in principle, an infinite number of different possible normal distributions, each one with a unique value of the mean and the standard deviation. Obviously, it's not practical to have an infinite number of normal tables. So the one that they choose to give you is the one based on the standard normal. All the other ones can be derived from that table through this formula. Okay, so this is actually a very important formula. Now, it's not such a big deal when we have calculators, but it's important to see how all the normal random variables out there are connected to the standard normal. So with this formula, we're assuming that X is normal. It could have any mean and any standard deviation. Okay, so that's what these represent. This is the mean of X. And this is the standard deviation of X. By doing this calculation, what the resulting value is called a z-score. And that is the equivalent location under the standard normal curve to what we're looking for with our X. So if you were still using tables, you could take any normal random variable and convert its results into z-scores and thereby use the tables. So now here, what we're going to do is continue with that example of the test scores, And we're going to ask ourselves the following question. What is the probability that our scores between 75 and 85? Now, that means, and by the way, you notice there's X in the middle. This represents the mean minus one standard deviation. This is within one standard deviation. So if we come down here, we can certainly calculate this directly. And we're looking at the lower limit of 75. The upper limit is 85. The mean is still 80. The standard deviation is 5. And if you type in those numbers, you'll see that you're getting 0.6827. Now, if you look at the graph on the right, you can see that we're actually asking for the probability of being within one standard deviation of the mean. Now, with the empirical rule, we use 68% as our approximation. Here we have the exact value, which is 0.6827. So this we already could have done without even doing the numbers, because this is the equivalent of, let me just show you quickly. If I applied this formula to each of the terms in this interval, then you can see that asking the probability that X is between 75 and 85 is equivalent to asking what is the probability that Z is within -1 to +1. By the way, I've got some graphs down here to show you why that's the case. Let's take a look at it. So with the top curve, that's our X, with a mean of 80 and a standard deviation of 5. The one on the bottom is our standard norm. So 80 up here corresponds to 0 down here, because that's the mean. 85, one standard deviation above the mean, is equivalent to a 1 in the standard normal curve. And then down here at 75, this is equivalent to a -1. So this area on top and bottom has the same area, 0.6827. So these two are the same thing. Now, I have compared this in the past, and I think this is a perfectly valid analogy to looking at the temperatures in Celsius and Fahrenheit. You're just converting one unit into the other when you convert one temperature to the other. It's the same principle. It's the same information expressed with different units. Okay, so 32 degrees Fahrenheit, as you know, would be 0 Celsius. It's the same information expressed in different units. Wow. So then, by the way, if you do come back, or if you want to double check this, even though we already know the answer is 0.6827, you can go back here and double check it like this. Okay, and also don't forget, these numbers are what we refer to as z-scores. So these are the z-scores associated or that are related to 75 and 85. So it's simply, the z comes from the fact that this is the standard normal distribution. Okay. Very good. All right, great. Now, the slides have their own example that we would like to look at. Let's go look at the slides. So we'll jump ahead a little, and we have a car dealer. Actually, I'm sorry, it's a tire manufacturer that makes tires, steel belt or radials. Now, we're being told here that the tires have a mean lifetime of 36,500 miles, and the standard deviation is 5,000. So we'd like to know the probability that any randomly chosen tire will have a lifetime of at least 40,000 miles. Now, it's funny, I just realized they didn't explicitly say that the tires' mileage is normally distributed. I guess this is meant to be a hint up here, but if you notice, they never quite got around to saying the words X is normally distributed, but that's what we're assuming here. So that means that here X is normal with a mean of 36,500 and a standard deviation of 5,000. With that information, we'd like to know the probability that X is greater than or equal to 40,000. So how do we do this? Well, it's actually very straightforward because we know how this is done. Go to your second vars and number 2 normal CDF. The lower limit of this interval we're looking at is 40,000. The upper limit is infinity, which again, when you type in is second comma 99, and that results in E99. Don't forget to change the mean and the standard deviation. And if you type in all that information, you should get, rounding to 4 places, a result of 0.2420. Okay, so about a quarter of their tires should last 40,000 miles or more. All right, so I'm sure nobody had any trouble with that one. And now here's a twist. They'd like to know how many standard deviations above the mean 40,000 represents. Or in other words, what is the z-score associated with 40,000 miles? So here's what we're going to do. We're going to take this new formula that we have, and we're going to use that to figure out the z-score. So if you notice, the mean and the standard deviation are taken from X. Remember, X has a mean of 36,500, and the standard deviation is 5,000. Those get plugged into my formula. The X depends on what problem I'm working on. In this case, I need to know the z-score associated with 40,000 miles. So when you plug these in, you'll get an answer of 0.7. So in other words, 40,000 is 0.7 standard deviations above the mean, and that means that these two probabilities are equal to each other. So if you really wanted to double check this, you could go back and here's what you would do. If you do all that, you should get the same number. There could theoretically be some rounding differences depending on how we calculate the z-score, but in this case, I don't think that'll be a problem. So we've got 0.7 up to positive infinity. 0 and 1 are the mean and standard deviation. And when you hit paste, you get, what do you know, it's 0.2420. So they mean the same thing. Okay. Now, unfortunately, they're going to throw a monkey wrench at us here. Oh, just what we wanted, a monkey wrench, huh? We're getting pretty good at this stuff, and now all of a sudden we have to think about something different. So let's go back and look at this scenario they're setting up for us. They're telling us the company wants to offer a guarantee for the tires. Let's say, they're basically saying, like, we guarantee the tires will last you X miles. Otherwise, let's say we'll give you another one. We'll give you a new one. But they don't want to have to give half the customers a new tire. So they're going to have to be careful where they choose that guarantee to be. If they guarantee, let's say, 50,000 miles, they may have 90% of the customers coming back looking for a refund. So they want to maximize that percentage of refunds at 10%. So we have to solve for the number of miles such that only 10% of the times will the mileage be less than that. So how in the world that, and here's what it looks like right here. So here's our 36,500 in the middle. X is the number of miles such that only 10% of the time or less should this number be reached, or should the number be that number or less. Okay, so these are the people who would get a refund. Anyone whose miles fall short of this X would get a refund or a replacement tire. Well, what we're going to do here then is a couple of things. We can take this z-score and let's see, where did oh, you know what we need to do here? We need to use a brand new function to do this. Okay, so up to this point, we've been given areas under the curve and asked to calculate their probabilities. So here, for a given probability, you can find the appropriate location under the curve as follows. This is what we're trying to do here. So now we need to go to our calculators and find this brand new function. So let's do this for the standard normal curve. There's some z-score which represents the bottom 10% of the distribution, but what is it? So if you go to your calculator for second vars, you'll see number 3 says INV norm, which stands for the inverse of the normal distribution. Okay. So now we have some thinking to do. What exactly are we trying to accomplish here? Now, before we go any further, I just want to point out here that not everybody's calculator is likely to be the same. There are different versions of the Chai 84 floating around. And so what I would like you to do is check this function and scroll down a bit and make sure that it's asking for area, the mean, the standard deviation, and the so-called tail, which means the tail area. If you have this option, tail, in there, make sure that it says left. And if it's not, you can scroll it over with your arrow keys and then hit enter to make sure it now says left. Okay. Now, if your calculator does not mention this option, that means it's been set up to use left. So that means you don't have to do anything. The calculators that do not show you this option are set to left. That's why we would like everybody to be doing the exact same thing. So if you do have this option, make sure it says left. Okay. Then it's gonna ask you for the area. Now, in this case, the area refers to the left tail. And based on this problem we're working on, that means the left 10% of the distribution. So type in area 0.10, change the mean and the standard deviation to 0 and 1. And what will happen is you'll see that it pops up with approximately negative 1.28 rounded to 2 places. What does that mean? That's a very good question. So if we come back up here to this graph, you'll see that, actually, let me change this a little bit. Actually, let me try this. I think this will be better. So in other words, what you just showed is that the z-score, such that 10% of the curve is below that point, is negative 1.28. Or you can think of it this way. The probability that z is less than or equal to negative 1.28 is 10%. Wonderful. Now, how does that help us solve the guarantee for the tire company? Good question. So I would like to point out here that this formula we had way back here. Let's go back when we first introduced it. Here it is. This formula implies that, let's see if we got some space over here. If I were to rearrange this algebraically, whoops, sorry, this is Z. That means that X equals mu plus sigma times Z. So that's what we're going to do right now. So we know all the numbers. The missing piece was the Z, by the way. We already knew the mean and the standard deviation. So if you plug in negative 1.28 for Z, you'll see that X is approximately equal to 30,100. So in other words, under this, with these tires, the mean is 36,500. And the cutoff point between the lower 10% tail and the upper 90% is 30,100 miles. And that in turn is 1.28 standard deviations below the mean. So the long and short of all this is that if the company guarantees that the tire will last 30,100 miles, then only 10% of the time will the actual mileage be less than that. And those people will be eligible for a replacement tire. So the bottom line is the company should guarantee that the tires will last at least 30,100 miles. This will result in no more than 10% replacements. That's what they're aiming for. They don't want to be overwhelmed, these requests for replacement tires. They want it to be a maximum of 10%. Wow, that was a lot of work. Now, luckily, it turns out there's a simpler way of doing this, which I'm sure you'll be happy to hear. And by the way, we will be doing this in Excel on Tuesday anyway, so you'll get another chance to see how this works. So down here, remember our original X, which represents the tires, the mileage of the tires. The mean was 36,500 and the standard deviation was 5,000. So what I'm going to do is use the same I and V norm function, but this time I'm using not this standard normal distribution, but the actual mean and standard deviation for this data. Now, if you notice, it didn't turn out exactly the same. That's because this 1.28 is only an approximation, but they're pretty close to each other. But this is actually the correct answer, 30,092.24 miles. If we guarantee that much, we'll only have 10% or more, 10% or less people will claim a refund or a replacement. All right. So that's what we need to say at the moment about the normal distribution. I think we're in pretty good shape. But remember, we still have to do all the Excel functions. So now we can turn our attention, at least for a few minutes, to this new function, the exponential distribution. This is the last one in this chapter. Now, we're not going to have time to go through it all the way. We're just going to introduce it. So what I'd like you to remember, first of all, I just want to mention here that this distribution is closely related to the Poisson distribution. That's the one where we're trying to model or calculate the probabilities of the number of events that occur per unit of time. Like, here's a good example. Classic Poisson problem. Assume that on average, 8 customers enter a store every hour. I can then go ahead and calculate the probability of any number of customers coming in the store over the next hour by using the Poisson distribution. But what if that's not what I'm interested in? Imagine it being reversed like this. What is the probability that the time until the next customer is 10 minutes or less, or between 10 and 15 minutes, or something like that? That is what when we use the exponential distribution for questions like that. Okay. So now, as you remember, every time we introduce a new probability distribution, we need to specify the probability function that we'll be using. And here it looks like this. Not too painful. All right. It's, it's certainly simpler than the normal distribution. I believe, yeah, here it is. And this is what the curve looks like. It's a curve that declines continuously as x increases. And there's some very familiar terms in here. For example, mu is the mean, which is the same mean that we saw in the Poisson distribution. So yeah, in other words, if for that problem with the customers, if an average of 8 customers come in the store every hour, that means that mu is equal to 8. E, remember that from the Poisson distribution, is approximately 2.71828. Now, this is a continuous distribution like the other two in this chapter, so we can only calculate probabilities for intervals. Okay, like what if we want to know that the time until the next customer arrives is between 10 and 15 minutes? That's fine, we can do that one. But if we try to do something like this, it'll just be 0. Okay, now there's calculating probabilities for single values gives us a 0 when they're continuous distributions. Now, I think I mentioned this before. Sadly, this one is not in the exponent the TI-84. If you look at that second VARS menu, you will not find this one. It's not there. They must have decided that the others are more important. I don't know. I think they may have misjudged a little, but all right. So that means we just have to do the algebra. Now you can see it's not really that difficult. Now here's the one thing we have to really watch out for, though. We have to make sure that our questions are consistent with the data that we have. For example, before I said that on average we have 8 customers coming in the store every hour. Then I asked the probability that the next customer arrives between 10 and 15 minutes. But if mu is in terms of hours or per hour, then what we have to do here is this. So we have to make the adjustment. We can't just leave it like that. Otherwise, our numbers will be way off. Okay. Hold on 1 second. All right. So notice you would enter it as okay. So that's what you'd be interested in. Um, and so this is how you would calculate it with this function. So anyway, this is as far as we got with the other classes. I don't want to push it too far because we're going to have to review a bit when we come back anyway. So what I'd like to do when we come back is run through the Excel commands and then in the process review these concepts. Then we can see how to do this exponential distribution in Excel, and then we'll do it with the calculators using the formula. And when that's done, we can move on to chapter 7. But we also have to think about a time and date for the second midterm because that one is based on 4 and 5, which we're done with. But that can wait till next week, I think, or the week after. I think you'll agree. When we come back from spring break, feeling all happy and refreshed, we'll start thinking about the perfect time to have midterm number 2. But we won't want to think about it today. It's Friday before spring break. Today, your job is to just have fun or finish your classes and then have fun. All right. So, if nobody has any questions, I'll see you all a week from Tuesday. Okay. So make sure you have a fun spring break.
Thank you, Professor. Have a good rest.
All right, later. All right, bye.
Thank you.
Okay, bye. You're welcome.